Nathan, a lot of people may not know specifically what a metamaterial is. So what specifically is a metamaterial?
Well, a bulk material or a natural material is some combination of the 92 naturally occurring elements that is mixed together. And we know about wood and steel and lots of other materials. But when it comes to how a material interacts with light waves, what metamaterials offers is an ability to have properties that you could not have with any normal material. And you get that by designing the material down at a small level. So a metamaterial has lots of little patterns on it. Those patterns can be programmed to interact with light in all kinds of different ways. And when I say light, that includes long wavelength light, which we call microwaves or radio waves, as well as shorter wavelength light that we call light.
What are some of the use cases? What are some of the real world applications that you're seeing or using and investing in when it comes to metamaterials?
Well, if you want high bandwidth communications and you want to send it wirelessly, you need to use a high frequency, which means you need to have a dish, and that dish needs to be pointed at the satellite. And that's true, for example, satellite TV. Well, there's some very expensive ways with having lots of gimbals and little motors that move the dish. In contrast, we have a company called Kymeta that uses an electronically steerable antenna. So the antenna itself, the working part's only a few millimeters thick. It's flat, and we electronically do the equivalent of steering to say we want to magnify signals, but only from this direction or that direction.
And so that's for high-speed internet. What about the infrastructure? Because obviously everybody currently is waiting for 5G and they think it's going to be better, faster. And you've also invested in a company that's in the 5G space and using metamaterials.
The challenge with any kind of wireless data is we all want it and we want to use a lot of it. And so cellular was the first idea behind doing that, where you could have different cell sites, and each site would use a different set of frequencies, but then you could reuse the frequencies that I'm using, 20 miles away. Well, as we keep getting denser in our usage, we have dense cities, we have a stadium full of people that want to be on their phones, and that's where Pivotal comes in. What they do is beam the relevant data towards the user, as opposed to flooding it in all directions, which is what a cell site does today.
And what about in the autonomous vehicle space? What kind of technology developments are you guys focusing on in that space?
With autonomous vehicles, obviously, you don't want to hit things. And one of the ways you can look out is with LiDAR. And we have a company that has a LiDAR, which uses lasers to scan the scene and find out how far things are away with zero moving parts. And that's amazing development. We also have another company that does it with radar. And radar lets you do that when you're in the fog. So we think both of those technologies are going to be very useful for autonomous vehicles, for drones, for a whole set of things where you want to make sure that you don't collide with something.
What does it look like from a cost perspective using metamaterials as opposed to common materials in applications like this?
You should think of a metamaterial a little bit like a circuit board for electronics. It does something you can't do any other way. So it's more expensive than if you just had a flat piece of an ordinary material. On the other hand, the flat piece of ordinary material won't do those things for you. You can have a curved metal parabolic dish for your data, but then you have to point it. So we think metamaterials are very cost effective when you compare them to the alternatives that you'd have to do otherwise.